So in this podcast, we're going to talk about net ionic equations. And this is primarily a topic for AP chemistry students. So if you're an honors or CP Chem 1 student, this may not be the best podcast for you. So in Chem 1, primarily the way we looked at chemical reactions was basically whatever was on the page. We had to write chemical reactions based on 5 types: composition, decomposition, single replacement, double replacement, or combustion reactions. And then once we wrote the reaction, we balanced the charges out for our products and reactants, and bam, we were done. But there's so many more levels of that in the AP that we need to focus in on. So let's talk about why we're doing all of this. And here's the fact. Even though we wrote it, it doesn't mean that everything undergoes some sort of change in a chemical reaction. And remember, the whole purpose of writing a chemical reaction is to identify the chemical change that's occurring. So let's look at this chemical reaction here. This is a very standard double replacement reaction that you do in a lab. This is lead nitrate added to potassium iodide, forming lead iodide and potassium nitrate. Now, you remember this hopefully from your Chem 1 days. This is where you take 5 drops of one clear liquid and 5 drops of another clear liquid, and you get this weird yellow precipitate inside of a test tube. And that yellow precipitate is the lead iodide. And you'll notice that on the left-hand side, that both of our substances are aqueous, but on the right-hand side, one of them is a solid and one of them is a liquid. One of them is aqueous. So we can see that the solid has undergone a change. And those two things that are in that solid are lead and iodide. So we can actually rewrite this reaction to eliminate things that stayed aqueous from left and right, things that did not undergo a change. So if we eliminate the potassiums because they didn't undergo a change, and we eliminate the nitrates because they remained aqueous from left to right, we actually end up with a reaction that looks like this. And this is what is called a net ionic equation. It only shows what's actually undergoing some sort of change. Lead and iodine go from being aqueous to being a solid, and that change of state indicates a chemical change that has occurred in the reaction. Potassium and nitrate are what are called spectator ions. As the name implies, they literally sit there and watch the thing go on. Whether they are there or not does not change the overall outcome of the chemical reaction. I could take potassium and replace it with sodium and still get lead iodide when I was all done. So potassium and nitrate are eliminated from the chemical reaction because they are no way, shape, or form involved in this chemical reaction. They are spectators. Because the lead and iodine change state, we write them. And we have to remember that primarily, we only are writing substances that undergo some sort of change in oxidation number from left-hand side to right-hand side. Okay? And I'm going to give you a whole bunch of rules that you're going to follow, and you're just going to keep referring back to these until you become experts on writing chemical reactions, that you just got to take out your notes and say, okay, where does it fall on my list of rules? Bam, there it is, and this is how it goes. So the real key to all of this chemical reaction writing at the AP level is identifying trends. If you can see the trend in the chemical reaction, it's 1,000 times easier to write the overall net ionic. Okay, so let's talk about these rules. Rule number 1 is you only write things that undergo a change in oxidation number or a change in state. We're going to talk about oxidation number specifically in class, so let's focus right now on the things that change state because they're the most obvious to see. Rule number 2. Solids, liquids, and gases are always written. No matter if they're on the left or right-hand side, they're always going to be written. So you notice that the lead iodide was a solid in the previous. That told me immediately that lead and iodide need to be written on both sides of the chemical reaction. 3, you got to know your solubility rules. So over the summer in your summer packet, you were given your solubility rules. Make sure you have those available because we're going to be referring back to them regularly. But these two are the most important ones. The number 1, sodium, lithium, potassium, meaning all your alkali metals. Ammonium and nitrate are not written if they're going to be aqueous. Okay? Now, there will be some cases where they will be written because they are solids, liquids, or gases on one side of the reaction. But if they're aqueous on the left and they're aqueous on the right, it's a dead giveaway. They're going to be eliminated. Also, your heavy metals. Your heavy metals are going to be written. Almost always. There will be exceptions, and I'll show you exceptions throughout class, but primarily your heavy metals like lead, silver, mercury, iron, and barium are metals that sit on the bottom half of the periodic table, and they tend to produce insoluble substances. And because they produce insoluble substances, that means they're going to be a solid somewhere, and it comes right back to this one right here. Solids, liquids, and gases are always written. Okay. Other things you need to keep in mind as you're writing these reactions. If you see the word heated, that means decomposition. If you see the word burned, that means combustion. Okay? There's a big difference between the two. If you see calcium hydroxide or sulfuric acid, the thing you always want to look out for is, are they concentrated, or does it say warm or hot? And believe it or not, it does make a difference. Remember, we're talking about ions here. And calcium hydroxide and sulfuric acid are both strong substances, a strong base and a strong acid, which means they should dissociate completely. But they only do that if they are warm or concentrated. And I'll show you examples of that later. If you see hydrocarbon combustion, they will always produce CO2 and H2O. So you've got to keep that in mind. Now, hydrocarbons are tough sometimes because they tend to involve organic naming schemes, and we won't deal with organic names until right before the AP exam. So I'm going to show you a way today how to still score points in the chemical reaction, even if you don't know what the organic name is. Now, keep in mind, anytime you see the word combustion, both here and here, we're talking about plus O2. Okay? If it's heated, no O2. It'll just be the substance, draw the arrow, and then the products. But if you see combustion, you know you're going to be adding plus O2 on the left-hand side. So it'll be plus O2 and then the arrow that will come after it. Okay. Now, what I want you to do is I'm going to put up all these decomposition rules onto the screen, but I want you to just write this down. Just pause the video right now and write this down, because I don't really need to explain these. I'm going to show you by example in class, but for right now, just click pause, copy all of this down. These are rules that you need to not necessarily commit to memory as much as practice this so often that they automatically become second nature for you. Okay, now I'm going to give you a couple more examples, and I again want you to pause the video and copy these down. Okay, so the reason I brought these up is these pop up often, and they can be mistaken for other reactions. For example, this one looks like a double replacement reaction, a metal hydride plus water. Notice that all of these involve water. Water is very popular. Oh, I'm sorry. This acid one doesn't involve water, but very popular. Metal hydride, metal oxide, metal and water. Always produce, notice the hydroxide on the other side. Now, here's the key with this, and this is what you got to be careful with those three reactions. Sodium hydroxide, lithium hydroxide are both strong bases. Because they're strong bases, they completely dissociate in water, which means that you wouldn't write it as NaOH, you would write it as Na plus OH minus. Same thing here. Li plus OH minus. And then what the final product will look like will be depending on what state of matter they're in. For example, a metal plus water, lithium's a solid. And if lithium is a solid, that means it will be written on both sides. Water is a liquid, obviously. It's not aqueous, so it's going to be written. So in this case, you would write everything. And I will show, again, lots and lots and lots of examples. Some of this may be very confusing now, and I'm going to be burning through this. But again, this is just boring notes so that we can spend class time actually getting into the heart of these chemical reactions and breaking down why these should be what they are. So let's go through 6 examples. Okay. Hydrogen sulfide is bubbled through a solution of silver nitrate. Well, hydrogen sulfide is H2S. What does bubbled mean? Well, obviously bubbled means gas. And if it's a gas, we go back to our rule. If it's a solid, liquid, or gas, we're always going to write it. So we know that we're going to involve H2S all the way through. No part of that chemical reaction is going to be eliminated. And then it says through a solution of silver nitrate. Well, silver nitrate is HgNO3 and is aqueous. Now, if you look at this, let's start by writing this like a Chem 1 student. This looks like a double replacement reaction. So let's switch our substances. We're going to end up with HNO3, aqueous, plus Ag2, S. Okay. Now, silver is one of those heavy metals, so there's a good chance that this is going to be solid. But I don't really know, and I don't really care about state of matter right now, because it's a gas here, which means that this silver, the sulfur, has to be written on that side. Now, let's look to see if anything doesn't change from left-hand side to right-hand side. Well, I can see that the hydrogen definitely changed, because the hydrogen went from being in a gas to being in aqueous. So that definitely has to stay. Sulfur changed because it went from being, it was a gas, and then it's in some form on the right-hand side. And now we have to look at the silver and the nitrate. Well, nitrate was aqueous on the left, and it's aqueous on the right, which means that it is going to go away. And remember what I told you about nitrate. If the nitrate is written aqueous on both sides, it's going to get eliminated. And that leaves us just the silver. And the silver, we're a little unsure of. It's connected to the thing that's a gas, which means that it must have undergone some sort of change to connect with that sulfur. So therefore, we're going to leave it. And let's eliminate everything that we need to eliminate. So let's eliminate those nitrates. Now, if we eliminate the nitrate, if we eliminate the -1 charge, we got to add the charge back on that silver. And the same thing here. Our hydrogen is going to be added. I'm going to erase this and make it a little bit bigger. And this is what we're left with when it's all said and done. This is our net ionic equation. H2S plus Ag plus yields H plus Ag2S. And that's our net ionic. We eliminated the thing that was soluble on the left and the right-hand side, the nitrate. Okay, let's go to our second one. Lithium metal is burned in air. Well, lithium is a solid because it tells us it's metal. Now, there's no formula for air. Now, if you wrote air in here, I'm going to have a serious talk with you, because we know that if it's burned, the only thing that's burned is oxygen. Well, I look at this and I've got a metal and a gas. And I look at this and I say, okay, that's a composition reaction. Now, is there anything that can be eliminated? No, because you've got a solid on the, lithium is a solid on the left, which means it's got to be written on both sides. Oxygen is a gas on the left, which means it has to be written on both sides. So this technically is the net ionic equation for this reaction. Okay, zinc metal, another solid, is placed in a solution of copper 2 sulfate. Okay, single replacement reaction. So my copper is going to come out. And we know that the copper is going to come out as a solid, because the zinc was a solid before. And we end up with zinc sulfate. So the zinc was a solid on the left, so it stays on both sides. Copper is a solid on the right, so it stays on both sides. Now we're just talking about the sulfate. Well, the sulfate was aqueous on the left because it's in a solution. The question is it aqueous on the right? Well, there's nothing that indicates that it doesn't stay aqueous, so it's going to get eliminated. And we add in our charges behind. And this is the net ionic equation for that reaction. Let's do a couple more. Okay, solid potassium oxide is added to water. Okay, it's a solid, so we know we have to write it, K2O plus H2O. Now, this looks like a double replacement reaction. And there's two dead giveaways that this is not a double replacement reaction. Number one, we go back to our list of rules that I gave you before, and underneath the metal hydride, on that list with the metal hydrides, was a metal oxide plus water. So anytime a metal oxide plus water, anytime a metal oxide is added to water, it's going to be creating a metal hydroxide. Now here's the other dead giveaway. In a double replacement reaction, you switch the two positive ions. If you switch the two positive ions here, you're going to end up with the exact same substance. Notice that our negatives are identical. Whenever your negative ions are identical, you know immediately that these things will combine together into one compound. Okay? So, especially when it's oxygens. So, when it combines together into one compound, we now get our potassium hydroxide. Now, here's the thing. Potassium hydroxide, potassium oxide has been added to water, so now this is aqueous. And potassium hydroxide is a strong base, which means that it's not going to be KOH, it'll be K plus OH minus, because that strong base will completely dissociate in water and turn into ions. Now, So let's go on to the next one. Chlorine gas, an oxidizing agent, is bubbled into a solution of potassium bromide. Now there's a lot of fancy words in here like oxidizing agent. You don't really know what that is because we haven't done electrochemistry yet. So let's write the reaction anyway. Single replacement reaction. So we're going to end up with this situation, the halide replacement. So we know the chlorine has to stay because it's a gas on the left-hand side. So that one's good. Bromine, now an oxidizing agent means it's something that's causing oxidation to occur, meaning a loss of electrons. Now I told you before, anything that undergoes an oxidation state change has to stay put. Well, if chlorine is causing oxidation, that means bromine must have to stay. So now we're left with just this potassium. And one of the rules was if potassium is aqueous on both sides of the reaction, it's going to get eliminated. So we're going to eliminate the potassiums. And we're going to add in the charges that are left behind. And that's a net ionic. Okay, now for our last example. Hexane is combusted in air. Okay, well, I know this is definitely a combustion reaction. So the question is, what the heck is hexane? So I know that I'm going to have a plus O2 in here because it's combustion. And so hexane. Well, I don't really know what the formula for hexane is, but it sounds weird, and it sounds like it could be an organic compound because they're not going to throw weird named ionic compounds in here unless they give us the formula. So hexane is probably a hydrocarbon, and all hydrocarbons produce CO2 and H2O. Now, the way this is scored on the AP exam is you get 2 points for the product and 1 point for the reactants when you write them. Now, here's the thing. Out of 3 points, without getting my reactants correct, I actually scored 2 out of my 3 points, which is 66% of my points. And if I can score 66% of the points, I get a 5 on the AP exam. So this is the type of thing that I want to do. Now, hexane is 6 carbons with hydrogens all the way around. So it's C6H14. So the formula is C6H14. It's actually 6 carbons, 2, 3, 4, 5, 6, with hydrogens coming off of the carbons, like this. Now, do you need to know this for this problem? No. Is it ideal that you can get the reaction right? Absolutely. It would be great if you could score all 3 points. But if you can score 2 out of the 3, that's what we're really going for because you want to score as many points as possible. So those are examples. Everything else we're going to do in class. So bring your notes, bring your solubility rules, and we're going to just write reactions like mad.